So here's part C of number 5 from the 2012 AB and BC exam, and in part C they say use separation of variables to find y equals b of t. So we've been dealing with this derivative, with this differential equation throughout parts A and B, which I have other videos for, and then in part C here it wants us to find the particular solution to the differential equation with the condition that was described way back at the beginning of the problem. So if we're trying to solve a differential equation, what we're going to do is we're going to separate our variables. So I'm going to divide both sides of this equation by this quantity. So I'm going to divide by 100 minus b, and then I'm going to multiply both sides by dt. So I'm going to have that 1/5 just kind of stay put. And our variables are separated now because we have the differential db in the numerator on the left, and that's the side of the equation that has all b's on it. And then on the right we have in the numerator our differential dt as well as any t's, and in this case there actually weren't any of those. Once our variables are separated, we're going to integrate each side in order to try to solve the differential equation, to get rid of the differentials essentially. So the integral that's on the right side of the equation here, and I'm going to actually write this result up here and kind of work down the right hand column. The integral on the right, the antiderivative of 1/5 with respect to t is going to be 1/5 t plus some constant c. So this antiderivative turns out to be this. We're going to fill up a lot of this space with this antiderivative. Might be easier to look at this antiderivative or this indefinite integral in this form because now you recognize that you have an inner function, this denominator, and if you let u equal that inner function, if you let u equal 100 minus b, your integral is going to then look like this, 1 over u, but you're going to do your antiderivative with respect to u, so you have to figure out what to put in place of the db. So compute the derivative of u with respect to b, so du db is going to be equal to, well, the derivative of this is 0, and then the derivative of negative 1b is negative 1. What are you going to put in place of the db? Well, multiply both sides by db, divide both sides by negative 1, and what you end up with is you end up with du divided by negative 1, or negative du, equal to db. So what you pick up here is you pick up db being replaced with negative du. What I'm going to do with the negative is I'm actually going to toss it clear out in front of the integral. And so if we continue to try to figure out the value of this, or the result here, going to copy my negative. The antiderivative of 1 over u is going to be natural log of the absolute value of u. I'm not going to put a plus c here. We're going to eventually try to solve for b. So I'm not going to insert a constant of integration on this side. I'm just going to let this account for the constant of integration within this solution. And I do need to back substitute though. So the antiderivative here ends up as negative natural log of the absolute value. U is equal to 100 minus b, so I'm just going to put that back in place of u at this time. So what we have as the integral on the left, the antiderivative on the left, is negative natural log of the absolute value of 100 minus b. Now, what you want to do here is solve this equation for b, and then also figure out what this constant of integration is. Now, the approach that we've taken in class has been to, when you have your dependent variable, which b is in this case, when that's inside a natural log that's within a set of absolute values, we've done some algebra to get rid of the absolute values and the natural logarithm before trying to find the value of the constant of integration. You can still do that at this point. It's a little bit dangerous because you have to kind of dance around the absolute values and be careful with your domain of your solution if you go that route. So we'll take the approach that I described initially, and that's let's solve this for b, get rid of the natural log, get rid of the absolute values, and then try to figure out what our constant of integration is. So my first step is going to be to divide each side by negative 1, and so that's going to leave us with this, negative 1/5 times t. Now I know if I divide this by negative 1, I get negative c. I don't know what the value of c is. I don't know what the value of negative c is. I'm just going to leave it as a plus c. I've done that a lot. Now I want to exponentiate on each side. Exponentiating will allow me to get rid of the natural logarithm. Now I haven't done anything yet that lets me get rid of the absolute values around the 100 minus b. but on the other side I'm going to have e to the negative 1/5 t plus a constant c. The reason why we still have to have absolute values on the left side of the equal sign here is because if you think about e to a power, e raised to a power is only ever going to be positive. You can do a little bit of algebra with this expression right here. You can rewrite it as e to the negative 1/5 t times e to the c. And the reason why I'm able to do that is because we add in an exponent when we multiply like bases. And if you recognize that e to the c is just some number, you can re-represent the constant of integration as a coefficient of this base e. Now at this point, although e to the c can't be negative, I can't get rid of the absolute values on that line, but if I just rewrite, and I'm not saying e to the c is equal to a, I'm re-representing e to the c as a coefficient of the base e. This coefficient could be positive, this coefficient could be negative. Since the right side of the equal sign, now that I don't just have a base e there, I have a number that could be negative times a base e. Since that's able to be negative at this point, I'm allowed to get rid of the absolute values and now continue to go about solving for b. Now to solve for b, what I'm going to do is I'm actually going to add the b to the right side of the equal sign, and then I'm going to subtract this exponential from the left. So I'm going to say 100 minus ae to the negative 1/5 t. That's going to be equal to b. So here's my general solution. We do want a particular solution or a specific solution. So what we're going to have to do to find that is we're going to have to utilize this condition. When t is 0, b is 20. So if we go ahead and put 0 in for t and 20 in for b, I think what we end up with here is e to the 0, which is 1. So we end up with 100 minus a equals 20. If 100 minus a equals 20, what's a going to equal? Well, I'm going to do the same thing I did a couple minutes ago. I'm going to add the a to this side, and I'm going to subtract the 20 from that side, and I'm going to get that 80 has to be my value for a. And so what is my specific solution written out? I could, I guess, write it as y equals. I'm going to write it as b of t equals. B of t, or b, equals what we have written right here in our general solution. So 100 minus, but no longer an a, we know what a has to equal. 80 e to the negative 1/5 t. And if you look at the solution the College Board presents, it might be slightly different from this. They might have done a slightly different sequence of steps to solve for b and or to solve for the constant of integration. But you will definitely have an equivalent solution on the College Board's rubric for the grading of this problem. And I guess before we wrap up the video, we should say that that equivalent solution would be accepted, and this would also be accepted. Equivalent solutions on AP exams on free response sets are always accepted.